Are they all related to Jeff? Like,
I'm not seeing any of Jeff's family here. So for those of you who don't know me, I'm J.D. Armstrong. I'm the Technology, Education, and Outreach Specialist here at the Institute for Astronomy. And one of the things I get to do is put together these public talks. And this month, with very little arm twisting, we've got Jeff Kuhn, who's the director. He'll be talking about whether or not the sun is shrinking and all these wonderful satellite observations that we're interested in. Now, Jeff is asked for a very short introduction, so we'll just say that he got his bachelor's at Kalamazoo Community College, his doctorate at Princeton. He has been into everything from martial arts to archaeology, and really found his interest in astronomy, where he mostly does solar work, but quite a few other areas of interest there as well. So let's give him a big welcome.
Welcome, everybody. So these are meant to be informal talks, and so you can throw things or ask questions at any time. I apologize for the room; it's crowded. I think all the windows there are open and the windows here are open, but we'll try to be short. Yes, sir. Already.
I read something that I'm hoping you'll touch on it.
Already, we haven't started.
And that is that what seems to track better with whether or not there's global warming or not is something called sunspots and solar, I think, magnetism, that it tracks far better than the level of CO2. I was wondering if you could comment on some of that. I don't know how good my story is.
Let's do that question at the end. All right? The issue of the connection of the sun to the climate is a really interesting one, and I think it's a pretty controversial one. And there's a lot of dispersion of opinion. And if you get me started, I'll go on for another 2 hours on that subject. So we'll get that at the end. Okay. Stick around and we'll do that. So
we have that talk on DVD if people want a copy of it.
Yeah.
But thank you, everyone, for coming. It's great to see folks interested in astronomy, and I think it's heartening to see that these informal talks are able to reach as many people as they do. Okay, all right. So the subject today is to try to understand whether or not, some people have said, as I'll tell you, that the sun is shrinking. And what I'm going to talk about today is that question and our answer to that question. And I guess we should start off by addressing the main question is, why should we care about the sun's size? Okay, so this is going to be a tough talk. There's going to be a quiz at the end. Throughout the talk, I'm going to be asking you questions. So look around to your neighbor. Only one of you will be awake at the end. Okay, so why care about the sun's size? It's a way of knowing about the inside of the sun that we can't see and how it changes. So one of my problems as somebody who studies the sun is to be able to get to the inside of it to know what causes it to vary. And so it turns out, as I'll show you, knowing the size of the sun tells us about the inside of the sun. Another really important reason is it may give us clues to how the Earth's climate will change over timescales of years. That's important to us. And that's kind of the question you're asking. I'm not going to have a lot to say about that, except for the 3-hour sequel to this after this. It's also a problem that has been debated for decades without any clear solution. And so the other reason why this problem is interesting is because we now have the tools to be able to answer that question in a pretty definitive way. So you should know that the Earth's climate is ultimately controlled by the sun, right? You know how it works. The sun gives off radiation, and the amount of radiation that it gives off, we're going to symbolize with this number L, which to astronomers means luminosity. And luminosity is just like the wattage of a light bulb. So a 100-watt light bulb has a luminosity of 100 watts. Well, it turns out that the sun is a big light bulb, and it has a luminosity of about 4 with 26 zeros after it. Okay? And that's the reason why over here at the Earth, we have, at some distance d, we have a temperature which is regulated not just by how much energy the sun sends to the Earth, but also how much energy the Earth radiates away, right? So there's this balance, and if the Earth didn't radiate energy away, even for the same amount of energy from the sun, what would happen to the temperature of the Earth? It would go up, right? So when we reach a balance between how much energy the Earth sends out into space, balanced by how much energy comes in, then we have the condition that we call equilibrium, which tells us the temperature of the Earth. Okay, and so the issue of carbon dioxide and what the climate of the Earth is has to do with these blue arrows and how much energy the Earth radiates. And carbon dioxide traps the energy and doesn't let it radiate as well, so the temperature goes up, even for the same amount of energy that comes in. But to know what the climate is doing, you have to know both parts of that equation. You have to know how much energy is coming in and how much energy is going out. Okay? But we can do that in principle, and if you do, if you build a model, you balance the in and the out, what you find out is that the temperature, the average temperature of the Earth should be, we use this funny scale based on absolute zero, 288 degrees Kelvin, which is, according to the Celsius scale, that's about 15 degrees Celsius. That's an interesting number because it's above zero. So the average temperature of the Earth should be above the freezing temperature of water. Of course, it's more complicated than that because it depends on the latitude on the Earth's surface. But basically, this is what tells us what happens with our climate. So there are two things we need to know. The one thing we're going to talk about that I know something about is this part of the equation, what the sun is doing. Okay? So what does the size of the sun have to do with that part of this? Okay. So it turns out if you take a filament, and the filament is the glowing part of a light bulb, and you make the filament twice as large for the same temperature of the filament, what do you think happens to the luminosity or the wattage of the light bulb? It's twice as much, right? Twice as much filament. Another way of saying that is that if you take a star, which is like a filament, the wattage of our star depends on the area of the sun and its temperature, okay? And so if the temperature of the sun were hotter, it would make more energy, or if it were a bigger star, it would radiate more energy because it would be like having a larger filament in a light bulb. And in general, we can write that as an equation, which isn't too important, but it basically says that the wattage or the luminosity is proportional to, okay, the area of a sphere is proportional to the radius squared. So that's really just area. So the luminosity is proportional to the area, and this you've got to take on faith. If you increase the temperature of something, it radiates more energy for the same area, and it's a strong function of temperature. It goes as the square of the square, or the fourth power of the temperature. So if you double the temperature of a log in your fireplace, how much more heat do you get out of that log?
4 times.
16 times. So you doubled it. It's 2 times 2 times 2 times 2, 4 times 4. Okay, if you have a log which was twice as big, you get twice as much energy. If it burns twice as hot, then you get that much more energy. So in the case of a star, it works the same way as the log in the fireplace. The size of the log is here, and the temperature of the log is here. Okay, so solar types, people that study stars, are interested in numbers that don't have units to them. I mean, they tell us about the mechanisms and the physics. And I'm going to be talking about a number that we call W. So the sun is changing. We're interested in talking about changes in the temperature or in the radius, the size of that star. And a change in the radius divided by the average radius of the sun, divided by a change in its luminosity, divided by the average luminosity, is this number W. Okay. So the quiz is coming up. Here's the quiz. There are 4 different stars. Which one has the largest radius? This one. Which one has the smallest radius? Well, these two have the smallest radius. Which one is the hottest?
Can't say.
Well, how do you know about temperature? The color actually tells you the temperature, right? So if something gets bluer or whitish, it has a hotter temperature. This is the hotter star. Which is the coldest star? This one right down here. So which of these stars has the smallest wattage or luminosity?
Red.
This one down here, right? And which one It has the highest luminosity. It's this one right up here. Okay, everybody passes. So what we're interested in doing, if we want to know the heat that comes into our planet, the Earth, is we want to know about both the radius and the temperature of the star. Okay, easy enough, except it's not that easy because it turns out the sun is a really pretty complicated ball of gas. Okay, so you know the sun doesn't have a hard surface. If we were to cut into it, we'd see that there are really three distinct layers. There's a layer that we call the core, and it's in the core where the energy is generated. Anybody know what makes the energy? Fusion. It's nuclear fusion. It's basically what happens in the core is we take hydrogen gas and we take 4 hydrogen atoms and we combine them to make 1 helium atom plus a lot of energy. Okay? And that's the only process that works for the sun. And this was only discovered within this century. For a long time, people thought it was chemistry. It was chemical reactions that produced the heat. Okay.
Last century.
Thank you. Last century. I'm behind the times. In the early 1900s. In the early 1900s, nuclear fusion was discovered, and up until that time, nobody could understand how the sun could glow for the age of the Earth was known to be much older than millions of years, yet the chemical processes that we knew could only last for a few million years. So it absolutely has to be that nuclear fusion takes place. Okay, put that into a computer model, and this is the picture that comes out. The inner core goes out to about 1/3 of the radius of the sun. Then there's a region outwards which is called a radiative zone. And all that means is that the gas which is being compressed from above it's not turbulent like the clouds in our atmosphere or the water in a pot of boiling water. In this region, the hydrogen is compressed, and the energy that's produced in the core has to filter its way out, and that's what this random line is. This is the path of a light, we call a packet of light energy a photon. And so a photon is created in the core, and it bounces, and then it gets out to a region which is the convection zone. And the convection zone in the sun is a place where the gas is boiling like it is in a pot of water. So hot gas here rises, reaches the surface where it cools, and then it falls back down again. So they're really distinct regions. The photon makes its way out and eventually leaves the surface where the sun becomes transparent. So basically, this light can't escape easily, and it's in this, we call it a random walk, because it's in material which is compressed. Well, in the core, the density is about 100 grams per cubic centimeter. You know what the density of water is? It's 1 gram per cubic centimeter. The density of lead is, 11, 12, maybe 18 grams. So the density of the core is compressed more than anything we have here on the surface of the Earth. Do you know how long it takes for a photon? So you know, for example, that a photon from the surface of the sun to get to the Earth takes 8 minutes. Right. How long does it take to go from the core to the surface? It takes about 1 million years. It takes about 1 million years because that photon bounces around so much between all of the atoms that are scattering.
So that's not like a function of gravity?
Well, gravity is the reason, because gravity has compressed all the material. So when you pack the atoms that close, that means it scatters a lot. So gravity is the reason, but it's really the scattering and all of the tortuous path that the photon takes that takes so long.
Does it bounce off of atoms or what?
It bounces mostly off of electrons. So down here, most of the material, which is the sun, is mostly hydrogen gas, is separate protons and electrons. So the atoms are torn apart. And so mostly it's bouncing off of those separate electrons, and it's mostly the electrons that determine the scattering.
Because there's more of them?
Because there's more of them, exactly. Right? Out here, the nucleus isn't torn apart. And so one atom of, say, carbon produces hydrogen, helium, lithium, beryllium, boron, 6 electrons, right, and only 1 nucleus. So you can see that you're going to get mostly electrons. Okay, so our problem is to understand the details of what's going on in here and why it can be that the sun might change its radius or change its temperature at the surface. So let's talk about radius and temperature for a minute. So it turns out that we actually have a pretty good understanding of the outer layers of the sun. We have good computer models that tell us how energy interacts with the matter that's there. And here's a computer plot. It's generated by taking a bunch of gas, putting it into a machine and simulating the effects of radiation and matter. And so this is I'm going to show you a lot of graphs, but this shows the temperature. So the inside of the sun is to the right. This is the temperature of the sun as it drops. And what I wanted to point out was that some magic happens right at the surface of the sun. So here's 10,000 degrees. Here's 16,000 degrees. The surface temperature of the sun as we see it is about 6,000 degrees, 6,000 degrees Kelvin, about 10,000 degrees Fahrenheit. There's a rapid drop in the temperature of the sun. It's as if somebody threw a switch as you move outwards, and all of a sudden the temperature, and this is what defines the surface of the sun. So when we look at the sun and we say, what's the radius of the sun? That's what we're looking at, this rapid drop in temperature. This rapid drop in temperature happens because at a certain temperature, at a higher temperature, electrons and protons are bouncing around so fast, they're a separate mix. They're a soup of electrons and protons. When the temperature starts to drop, all of a sudden, they can recombine. And when they recombine, we don't have all of those free electrons and free protons to scatter the photons. And so what happens is, when this happens and the hydrogen recombines, all of a sudden the atmosphere becomes transparent. And this is where all of the photons escape. Okay? So in the case of the surface of the sun, it's really hard to change the surface temperature, because every time you do something, the sun becomes transparent at about the same temperature. Let me show you what that means.
That's your defining edge.
That's the edge, where that sharp transition is, and where the sun becomes transparent, right? Until that point, the photons have been bouncing around for 1 million years, and they can't get out. We don't see them. They get to a certain point, and all of a sudden, the hydrogen locks up with the electrons. There aren't as many things to scatter, and those photons escape. Well, here's an interesting plot. This shows when the sun was formed. It formed out of a big cloud of gas. And we're, in our solar system, we think we're about 5 billion years old. So we're about right here. And this is a graph that shows the wattage of the sun measured relative to current wattage. And so we're right here where it's 1. And from this graph, you can see that when the sun formed, was it less luminous or more luminous than now? It's actually less, right? Since this curve is lower here. So this is the beginning of the sun. And then according to our understanding, the sun is actually getting brighter as it gets older. Okay, there's a reason for that. And if you studied some chemistry, it has to do with the ideal gas law. We're continually taking hydrogen and forming helium. But we start with 4 hydrogens and make 1 helium. So the number of particles in the inside of the sun is doing what? It's decreasing. It's decreasing, but the pressure is still the same. The total amount of weight is still the same. So if you have a smaller number of particles, the central temperature of the sun actually has to go up by the PV equals nRT law, and I won't go through that. It's basic chemistry, and as a star gets older, it has to get hotter. And so what you see here is from the beginning to now, the sun has gotten about 30% brighter than it used to be. What do you think has happened to the temperature at the surface? Not very much. Well, the temperature's gone up a little, but look at this graph. Here's 5,600 degrees, here's 5,800 degrees. 0 is way down here. Okay, so the temperature of the surface of the sun, so here's where we are now, has only gone up by less than 200 degrees. And so the fractional change is less than 1%, okay, or about 1%. So there's a 30% change in the radius of the sun, in the luminosity, but the temperature hasn't changed very much. That's just another way of saying that those photons, when they come to the surface and all of a sudden it gets transparent, you can't really change that temperature very much. It's determined by the physics of at what temperature the protons link up with the electrons to form the neutral hydrogen. Okay, so that's summarized here. It's hard to change the sun's surface temperature for a constant temperature, W, remember that number, W is the change in radius divided by the change in luminosity. So W, we expect, if we understand our physics, should be 0.5. So if you change things in the sun, because it's so hard to change the temperature, the fractional change in the radius divided by the fractional change in the luminosity should be 0.5. Okay, by computer models, it's 0.45. What that means is that over this time where the sun got 30% brighter, the solar radius should have increased by 15%. So the first answer to the question is, could the sun be shrinking, is no, it shouldn't be shrinking. It should actually be getting bigger in time. Because the evolution of the star, where it takes energy from the core by combining protons to make helium, forces it to get more luminous and to swell outwards because it can't change its temperature. So think of it that way. The sun has to release more heat, but it can't change the outer temperature because that's determined by the chemistry of hydrogen. So the only way it can get brighter is to get bigger. Okay? So that's what we expect. That's our understanding. That's what should happen in the sun. Okay, is that what happens? Well, of course, it's more complicated than that, right? Otherwise, I'd be done and go home.
We could talk about global climate change.
So the real sun is over here on the right, and that was taken back in 2003. And I just wanted to show you a movie. This is several days, actually several weeks, and it shows the evolution of the surface. And it shows a couple things. One is the sun rotates. So you should know that the sun takes about 28 days to rotate. It takes about 28 days at the equator. It takes about 31 days near the pole. So actually the sun is differentially rotating. It's shearing. These things that you see here are sunspots. And the sunspots are dark regions that we think of as magnetic storms. They're not fixed. You can see, in fact, this thing that grew over here produced in November. We call it the Halloween solar flare. You remember that one in 2003? It's the biggest solar flare we've ever recorded. It for a long time wiped out communication to airplanes over the northern polar regions. It wiped out a couple of communication satellites. It had an effect on the Swedish power grid. It was the biggest solar flare that we've ever recorded. We think there was one larger back in the time of Carrington, before we had satellites or even routine observations of the sun. In the 1860s, when telegraphs were being strung across the United States, there was an event wherein spontaneous fires were generated over long expanses of copper wire that was what was in the telegraph. People were injured by these fires, in fact. We believe that was caused by a solar flare larger than this one. But this one was the largest. And it's associated with these things that are called sunspots. Okay, you should also know that the sun has a rhythm to these sunspot patterns. And the rhythm is not very regular. It's not like hitting a tuning fork, which has a certain frequency, or running a violin string. This shows the number of sunspots from when they were discovered, basically by Galileo in the West. Galileo had a telescope. He projected an image onto a card, and he started this game of counting sunspots. And since then, the number of sunspots has been recorded, and it shows a pattern. And each one of these peaks happens with a separation of about 11 years. So every 11 years, there's a bump. But it's not a very regular bump. At some places, like in here, sunspots weren't observed. In the 1800s, sunspots weren't observed. We have a problem right now. We may have to go out of business. The last solar cycle has been unusually long. We're waiting for something interesting to happen on the surface, and it's just not coming. This solar cycle has been the longest period of uninterrupted boredom with nothing happening for about 70 years. So we have no idea what makes this rhythmic, almost 11-year cycle happen the way it does, but it's clearly part of the connection between the sun and the Earth's climate. Okay, the solar rhythm.
Are you saying that the graph would show nothing over that 70-year period?
Back here at the Maunder minimum?
That's it.
There was nothing. There was it was more like a 30-year period when there were no sunspots.
Did you say it was right now also no spot? No sunspot?
There are, how long has it been since there have been a couple of spots that have appeared over the last couple of months.
Oh.
But for about 4 years,
Wow.
3 years, we haven't seen much of anything. And it's very unusual. A number of my colleagues have been predicting that we would have a very large solar cycle that would happen years ago, and we're completely wrong. Completely wrong. Okay. Okay, the other thing I should say is we're going to be talking about the radius of the sun, the size of the sun. The radius of the sun is about 700,000 kilometers. Astronomers like to measure not so much the linear distance, but the angular size, right? Do you know how big the sun's angular size is? It's about half a degree, right? Which corresponds roughly to your thumb at arm's length. That's about half a degree. We also tend to measure size, angular size, in units we call arcseconds. An arcsecond is about, at a very good astronomical site, an arcsecond is the angular size that the atmosphere limits our ability to see angular detail. So an arcsecond is about the blurring size of an object which is infinitesimally small, just a point-like object. So an arcsecond is a convenient unit that way. And in those units, the radius of the sun is about 1,000 arcseconds, or 960 arcseconds. Although the angular size of the sun changes, right? Because we're in an elliptical orbit, and so the size of the sun varies as we get closer and further away to the sun. Are we closer to the sun in the summer or the winter? Good. Right? It's not the distance from the sun that makes the seasons, but it's the tilt. Right? We're actually closer to the sun in the winter. Okay. Right. That's a good point. Yes. We are we. Okay. So here's an interesting puzzle. Here's a really interesting puzzle. So since about 1978, we've had reliable measurements of how bright the sun is. These are satellite observations taken from above the Earth's atmosphere. And there's a bunch of them. And these are measurements that tell us the total amount of energy per unit of area that the sun radiates at us. And they go back, so this is before 1978, and this goes to 1999, but we have measurements that go beyond this. And each one of these colored sets of points is a different satellite. And what catches your eye when you look at these measurements? Well, for one thing, they don't agree very well in absolute value, but that's okay. That's a calibration issue. It's really hard to make an instrument that has an absolute calibration. Most instruments are good at measuring changes. So in the Akram measurement, that change is absolutely believable, and in fact, it agrees very well with that change right there. Okay, if you collapse all of those on top of one another, you get what you think is a reliable record, we certainly believe, of the solar, we call it the solar radiance. So it's adjusted to the average position of the sun to the Earth. So we've taken away this effect of the ellipticity of the Earth's orbit. And look what it shows. There's this 11-year period, right? The sun gets brighter every 11 years, reminiscent of the sunspot cycle. So what do you think? Should it be brighter when there are more sunspots or less? Sunspots are dark, so the dark spots mean that they're dark only because they're cooler.
But they generate more UV.
The ultraviolet comes from higher in the atmosphere, above the sunspots.
Right, but the sunspots generate more UV than the rest of the sun. So the spectrum changes.
It does. The ultraviolet part of the spectrum is if you look, so add up all the energy. The ultraviolet part of the spectrum is a tiny fraction of the visible part. So if we're talking about the total amount of energy that the sun radiates to us, it turns out you might have expected that it should be greater when there are fewer sunspots. Okay, here's 1989. There's a peak. here's 1980, or sorry, 1990 and say 1980, roughly 10, 11 years. It's a peak there. If I go back, you can see that the peak in sunspots, so these are 10-year increments, there was a peak in sunspots at 90 and at 1980. So the sun is actually brighter when there are more of these dark spots on it. That's a problem. We don't understand that either. Some people think, well, it's because there are lots of other things around sunspots that are slightly brighter, but that's not right. We know that's not right. It has to do with something that goes on inside the sun. It's another part of the mystery. In any case, the brightness of the sun, if we believe that it's the wattage of the sun or the luminosity, is going up and down with this 11-year cycle. And that 11-year cycle, turbulent mixed.
What's a sunspot?
All right. Okay, if the brightness changes at the Earth are from real solar luminosity changes, so that brightness amplitude, I should say, is 0.1%. So that little bump isn't a percent, it's only 0.1% of the average brightness of the sun. So remember what W is. It's the ratio of the percentage change in the radius to the percentage change in the brightness or the luminosity. So what should the radius change of the sun be if we understand the physics of what's going on? Well, W is equal to 0.5, which is a half, and so the radius change should be half of that 0.1%, which is 0.05%. So there ought to be, if we understand anything, a 0.05% change in the radius of the sun. The radius of the sun is 1,000 arc seconds. That means we should see a 0.5 arc second change. 0.5 arc seconds is about 300 kilometers. So the sun, if we understand anything, ought to be going in and out with a radius change of 300 kilometers, but it's 700,000 kilometers in radius.
Quick math question.
Did I screw up?
Isn't half of 0.5 0.25 instead of 0.05?
So, sorry, the luminosity change is 0.1%. So this is 0.1, and half of 0.1 is 0.05. So,
Okay.
So I've already put the half in there before I wrote the 0.05. But thanks for keeping me honest. Okay, so how do we measure the size of the sun? That's finally I'm getting to the point of I do measurements, and how do we do it? So we can look at eclipses. And I'm not going to talk about any of these except for this last one. You can look at the moon as it passes across the sun and measure the time that it takes. So the time between that first occurrence of the eclipse to the end of the eclipse. And those numbers are known for years and years, a couple hundred years, and that's in principle a way of knowing the size of the sun. You have to know a lot about the orbit of the moon and the orbit of the sun to make that work, but some people think we know that. Meridian timing, you can look at the sun as it drifts across the sky and it moves at a constant rate, and you can set up an instrument, basically, that looks at the crossing of the east limb and the west limb of the sun, and you take your stopwatch out and you measure those events. And if you know the rate at which the sun is moving, then you can measure the angular size, and then you correct for the distance from the Earth to the sun, and you can get a radius. An astrolabe is an instrument which measures basically angles in the sky. You can set up an instrument that measures angles. The transit of Mercury. Occasionally, Mercury moves across the image of the sun. And if you have very good measurements, you can measure the timing between Mercury crossed from one side of the sun to the next. And if you know from we call it your ephemeris, from the orbit of Mercury, if you know how fast it moves, you can get the size of the sun from that. Finally, you can make a direct image of the sun. And you can take out your ruler, hold it across the image, and pull out the size. Well, you don't really use a ruler, you use a bunch of other tricks. But basically, it's look at the image and measure its size. Okay, so here's the reason so Marcello's with us. Marcello is a colleague of mine that's been involved in this for a long time. We have been struggling with this problem that many people think that the sun is shrinking. And it comes from the meridian observation. So here's the time scale here. So notice 1700. How could we have real measurements in 1700? Well, there are. I didn't investigate them, but they're based on solar eclipse timing. And each one of these is a different set of measurements. And the scale over here is the change in radius for those measurements over that time. So let's look at these points. So the measured radius of the sun fluctuates plus or minus a half an arc second. Okay? That's a pretty good measurement. Remember, the radius of the sun is 1,000 arc seconds. So that's a measurement of sort of, what is that? A half, it's 0.05%, right? That's comparable to what we expect the solar cycle to show to us. Remember that 11-year cycle, and the brightness we think should be a 0.05 or a 0.5 arc second change. These are too noisy, there's no trend in those. The Mercury transit data has a little bit of a trend to it downwards. The Mercury transit data from Parkinson has a trend downwards, although it's got lots of noise. And the eclipse data has a trend downwards. And the sort of errors in these observations are all at the level of sort of half an arc second. It's not surprising it's half an arc second, right? Because that's kind of the scale where the atmosphere of the Earth is a problem, where it produces twinkling and blur. So this is what we want to address. Is it really true that contrary to our understanding of the physics of the sun, which means that it should be expanding in size, it's actually shrinking at a rate of 50 milliarc seconds, so 0.050, I'll use milliarc seconds once in a while, it's 0.05 arc seconds. Each of these curves ranges in downward trend from about 0.05 to 0.2 arc seconds per century. That's the number that some people claim. It's a tiny number. Here's another set of measurements, which is a compendium of a lot of ground-based measurements. I think these are Astrolab Marcellos here. Are those Astrolab Marcellos?
No, I think solar eclipse.
Okay, solar eclipse or Astrolab. In any case, it's a bunch of them. And this analysis said, hey, the sun goes through another cycle, which is 76 years. And notice the scale over here. Here's minus 0.5 arc seconds, and here's 0.5. A lot of noise, but if you average those points, there's this curve. And do you believe that there's a 76-year period? I don't know.
Statisticians think so.
Statisticians think so. I'm going to show you some data that was taken from space over this period of time, and which should have shown this downward trend if this curve is right. Okay? The other thing that came out of this analysis was that there was some suggestion that there is an 11-year fluctuation in the radius of the sun, such that the sun is smallest at the peak in the sunspot number with about 1/10 of an arc second between the peak and the midpoint in the cycle. Okay, so what does that mean? It just means that actually that measurement that I just quoted is inconsistent with a bunch of other measurements. Depending on when you did your observations, some people thought that the amplitude of the 11-year cycle in the radius fluctuated from 0.4 arc seconds down to minus 0.25 arc seconds. So not everybody agrees. It's a bit of a mess. Not only that, I should point out to you that not everybody agrees on what the radius of the sun is. Again, it's a bit surprising. If you ask any number of different astronomers how big the sun is, well, they on average say it's about 959.5 arc seconds, but the measurements fluctuate around that number. And this is just a measure of the fact that it's really not easy to make these measurements from underneath the atmosphere. Why is it not easy from underneath the atmosphere? It's not easy because of this effect. It's coming.
I'll never criticize a weatherman again.
Oily atmosphere.
A weatherman, well, it's true, they have a hard job.
This is what a picture of a star looks like through the atmosphere. Okay? And so this is the angle in the sky here is about an arcsecond. Okay, so that's what I was talking about. So you never get to see this because your eyes aren't that sensitive. But if you took a telescope that could take a real rapid snapshot, you'd see that what the atmosphere does to us is blur out things that should be very simple and look like a point into things that are a confusing mess that looks like that. That's really our problem. And that's the reason why, for so long, we haven't been able to solve this problem of what the sun is doing. All right, so let's solve that problem. How do we do it? Exactly. You get above the atmosphere. If you get above the atmosphere, then the limb of the sun, the edge of the sun, doesn't get bounced around like that picture I showed you. And if you have a sensitive, like a CCD detector, the only thing you have to worry about is how accurate you can measure the brightness on your CCD detector. So let me tell you about how we're doing this. This is a really long-running experiment. I date this experiment. So the first meeting of the group of scientists to build this satellite happened on the day my daughter was born, and she's 26 years old. So the experiment goes back 26 years. I missed that meeting, by the way.
Good answer.
It was a good answer. So there are a lot of folks that have been interested in the problem of astronomy. Marcello is here. He's been working with me not 26 years, but we started a bunch of years ago on that. Folks from Stanford, which have been responsible for parts of the satellite, are part of this group. We have scientists from other parts of the IFA. Actually, JD may not remember it, but when he was doing his PhD, or before he got it, he actually worked on some of this stuff too. And these are other scientists from the old days who were involved in trying to understand how to measure the size. This is the satellite. It's called, well, the experiment is called the Michelson Doppler Imager, and it's aboard the equivalent of the Hubble satellite for solar physics. It's not called Hubble, it's called SOHO, the Solar and Heliospheric Observatory. And it's been up in space working quite well for about 12 or 13 years. And we've been using it over that period of time to make the measurements I'm going to show you. This is the instrument that actually does the measurements. So this was when the system was being integrated at Goddard. That's what it looks like out in space. And just to prove to you that it really is in space, I have a simulation. There's the sun. There's our satellite. This is the Earth and the Moon. And so that's kind of a cool place to put a satellite, right?
That's very cool.
Because that satellite is actually further away than the Moon, and it's at a place in between the Sun and the Earth where gravity balances from the Earth and from the Sun. So if you put a satellite out here, you don't have to have thrusters to keep it in the same position. If you set it up in this little orbit right here, which is about the same size as the orbit of the Moon, that's called a halo orbit, it sits in between us and the Sun, and it can look at the Sun continuously. That's a wonderful thing, and there's no atmosphere. It's just a perfect place to do science.
May I ask why its orbit is perturbed like that? You're showing it shifting.
That's the magic of orbital dynamics. If you put a satellite right at that balance point, it turns out not to be stable, and it wants to move around. So the truth is, if you want a satellite to stay in roughly the same place, it has to kind of orbit around that stable point. So the Earth is here, the Sun is here, and SOHO actually does this little orbit here. It takes 6 months to go all the way around that orbit, not 12 months. But so it does 2 of these orbits in the time that it takes to go all the way around. This is a confusogram. It shows all of the optics in the telescope, and it's meant just to show you that there's a reason why this instrument costs about $150 million. Well, one of the reasons is Lockheed built it. But the other reason is that it was designed to be able to look at the surface of the Sun and measure the motion of the gas, to do something, to measure what we call sound waves moving back and forth at the surface, to do something that we call helioseismology. And we came along and said, hey, this is the best way to measure the solar radius, and convinced the organization to do the experiments that we talk about in just a second. But it has a lot of stuff in it, and part of that stuff is not good for measuring the sun's radius. And I'll show you what it does to us. In general, what we're doing, so we're measuring the sun's radius by taking an image and putting a ruler across it, counting the number of pixel units in the diameter. The ruler we're using is a computer, right? And the computer does all the analysis. And we won't get into that, except to say that our CCD has 1,000 by 1,000 pixels. It's an old one. This goes back to the 80s, and in other words, it doesn't have as many pixels as your camera does now, or your cell phone. We extract an annulus of pixels around the edge of the sun, and the brightness of the sun does this sort of thing right here. So we analyze that in a very sensitive way, so that we can see tiny motions in the position of that limb, which corresponds to the place where that hydrogen gas is becoming transparent, and that tells us at every location around the edge of the sun where the edge is. And from that we can get the size of the sun. We can also get something else, right? We get the shape of the sun. Okay, so what do we learn from that? Well, we learned that the sun is remarkably spherical. It's flattened by only about 6 kilometers out of 700,000 kilometers. That's really amazing. In fact, I just happen to have a model of the sun right here. This ball bearing, so it turns out if you buy a ball bearing, they're graded. If you get a grade 300 ball bearing, that means that the out of roundness of the ball bearing is 300 parts out of a millionth of it. 300 over a million inches. That's pretty small, right? A millionth of an inch is a tiny number. For those of you calibrated in microns, it's what is it? It's 0.025 microns. This ball bearing is not very good, but this ball bearing is not as round as the sun is. Okay? And the sun is rotating. The out of roundness of the sun is really due to the rotation. But in the process of studying all of these images, one thing that we discovered was that the sun actually has a very unusual bumpy pattern on it. In fact, I have a picture of the bumpy pattern. There it is. That's what the sun looks like under significant magnification of the surface. Significant because these bumps, remember we were talking about the out of roundness of the sun is about 6 kilometers. These bumps are 100 meters. But we can find those bumps by looking above the atmosphere and over a long period of time. So those bumps are at a level much, much smaller in relative terms than any ball bearing we could make in the laboratory.
How many bumps are there?
Oh, I don't know.
Are they all the same size?
They appear to be all the same size. And you should ask, what is that from? And we discovered that we're not Earth scientists, but there's an analog on the Earth. Anybody know what it is? It's called terrestrial Rossby waves. It turns out that since the early 90s, we've had satellites looking down at the ocean surface. And this is a color plot, so obviously this is where there's not water. But if you look at the ocean surface and you average over a whole bunch of waves, so you can get the average height of the ocean, that on the scale of, and I don't have the scale here, on the scale of a few centimeters, the ocean surface has bumps. Right? And the ocean, where it's red, is deeper, and where it's blue, it's higher by a few centimeters. And in fact, there's a movie here. Taken over many, many months. And so what you see in that is that those bumps well, you saw it, right? Yeah. Those bumps over periods of months are migrating from the east to the west. And those are called Rossby waves. So the surface of the ocean also has bumps, like the Earth does. And they're caused by the fact that it's caused by the rotation of the Earth. in the environment of the surface. There's a big density difference between the air and the water. That allows for the existence of waves and Rossby waves, and those bumps live for many months as they travel from the west of you. They're not waves. You'd never see them because they're much too small. But they're the analog of what's going on in the sun. So we think that was pretty cool, and we think we understand it. So that takes us finally to what is the radius of the sun doing. And that's kind of a long, I thought it was an interesting story. You might be bored by it, but I'll try to give you some sense of adventure. So when you first look at the radius of the sun from the satellite, what you see, this is just from 96 to 2008. You see that the radius of the sun, these are arc seconds, does this, and it seems to jump. And then it has this wiggle pattern here. So the period of that wiggle is 1 year. What do you think that is? That's due to the orbital effect of the Earth and the satellite, which is out beyond the orbit of the moon, getting closer and further away from the sun. These jumps are instrumental issues. We weren't the first priority in the satellite. And so periodically they made adjustments in the focus of the instrument that changed the size of the image. We hated it. But it turns out we can compute exactly what that is due to, and we can take it out. And if we do, we then have to deal with some other issues. So the other thing that we found out was, so the instrument was built with a bunch of so it's continuously in contact with the Earth, and the scientists at Stanford and Goddard, and we get a running readout of the temperature of a lot of different things. So the temperature in Celsius, it's pretty hot out there, right? So the front window, that's the big piece of glass that the light goes through, has a temperature that goes up and down by 4 or 5 degrees. And in fact, when you get inside the spacecraft, so there's a window and then you get into the instrument, the temperature is a little bit less, but not a lot less. It's only 3 or 4 degrees. And the primary lens has a fluctuation and a jump, and the secondary lens has a fluctuation. And we can measure the focus, so we know that as we adjust the instrument, we can focus it, right? We want the sharpest image we can. And so the focus, the best focus, is also changing over years of time out there in orbit. So there are lots of things going on, and they're not all good things. A lot of them are complicated and things that we worry about. This is a big one. Why do you think the temperature is changing on that cycle of a year? It's getting further and closer to the sun, right? And you get closer to the sun, and you get more energy, right? Just as if the Earth got closer to the sun, the Earth would get hotter. It's the same effect. This jump right here is where somebody said, "Oh, let's tweak the heaters inside the spacecraft." Well, they tweaked the heaters inside the spacecraft, and the temperature jumped up, and they left it there for a couple of years, and then it jumped down. It turns out that was a really good thing, because we knew how much we heated it, and we could calibrate our measurement of the effect on the radius. So here's what we learned. These are plots of the change in the radius of the sun. And Marcello just worked this out, and these curves go all the way out to 2010. So if we don't understand the instrument, and we just take the radius that comes out after we adjust for those big jumps, it looks like the radius of the sun has a 1 year cycle to it with the big jump right here. Okay? We need to understand the instrument. We spent a year with a complicated mathematical model of the optics, and then we took the calibration data and we worked out what change in temperature corresponded to what apparent change in the size of the image, right? We have an instrument that's making an image, and if you change the optics, you'll change the size of that, and that doesn't have anything to do with the sun, it just has to do with changes in your instrument. So that big jump,
Gave you a calibration there, didn't it?
and that calibration was wonderful, because we knew, and we could see what it did to the radius. And by the way, we could actually go back to an optical model and show that that's exactly what it should have been.
Good control.
Or just lucky. So what came out of that was then this curve, but this curve didn't correct for a change in the long-term focus. So it turns out that that front window over the course of 11 years used to be a pristine piece of glass that was crystal clear. After 11 years, it was black. And we're getting only about 30% of the total amount of light that we started with. So more and more energy is being absorbed in that front window. That's because of the radiation damage in that environment.
UV, basically, I guess.
Yeah. And the particle flux and color centers and other
Is that a
things.
quartz window?
Don't know the answer to that. We can look it up for you. But the net effect is that there's another trend in the instrument, and we used the focus information to be able to actually understand what that was, and we could take that out. And look what's left. So now this is our measurement of the solar radius, where we've taken away the instrumental effects. And here's a scale, that's 0.6. Let me show it on another scale. Okay. This is all of the data. This is a running average of the solar radius. This is 50 thousandths of an arc second. Here's 0.1 arc seconds. And we can say, beyond a shadow of a doubt, that there is no 76-year period. You might ask, well, okay, so it looks like something's going on. And notice we didn't do a perfect job. There's still this bounce here. There's still some one-year effects in the data. There's still things going on that we don't completely understand, but they're relatively small, at least on the scale that we've plotted here. So an interesting way to look at this then is to look at the sunspot cycle on the same curve. Okay, so here's what the solar radius is doing. Here was the peak in sunspots, sort of a double peak back in 2000 and then back in 2002. Nothing going on since back in here. And the peculiar thing is that this dip, apparent dip in the solar radius, isn't correlated with either the peak or the trough in the sunspot number. So we think that this basically represents our limit in our ability to understand the instrument. It's not a real measurement of what the sun is doing, but it's so small that it rules out all of the other ground-based measurements. Okay, so what can we say about the average slope of that? Well, we've only got 11 years, so it's hard to extend that over a century. But we know that the trend for a shrinking sun has to be less than 0.3 arc seconds per century. The solar cycle has to be less than 0.03 arc seconds. If we understood the solar cycle, what did we think this should be? You remember? 0.5 solar second, 0.5 arc second. So beyond a shadow of a doubt, we've proven that we're confused. That's good. That's good. That's something to think about and understand. We don't understand the solar cycle. Okay? The sun's apparent irradiance is changing, and it's apparently not due to a shape change, which it should be, if we understand that physics. There's no 76-year cycle. There's no solar cycle change. The shrinking sun is not ruled out, but it's not supported. And of course, what that means is that we have to do better. Another satellite. Oh, you stole my thunder. There it is.
Can we measure other stars and other things to help determine what's happening?
That's a good idea. And we can see other stars change their brightness, but we can't measure their size because we can't actually see them. They're not close enough to see. In February 9th, it's coming up, on an Atlas V is a launch of what's called the Solar Dynamics Observatory. And this satellite is designed to do astrometry. Solar astrometry is the subject of measuring the size of the sun. So with this satellite, we will answer once and for all whether or not the sun is shrinking over this long period of time. We've already answered that it's not changing its shape on this other scale. And hopefully we will, with this information, be able to go back and understand what is the magic which is causing the sun to change its irradiance with this eurythmic pattern that's close to being 11 years.
How sensitive is that one?
Well, this one will end up being about an order of magnitude more sensitive. This set,
0.01 arc second, maybe?
well, so an individual measurement that we make is sensitive at the level of about, so we measure the radius in a single measurement at about 1,000th of an arc second. This is about what is that? 100 micro arc seconds per measurement. So the limitation has always been the systematics, though, right? I showed you what we had to go through to be able to understand what the instrument is doing. This satellite will actually do a roll every few months, which is what we need to be able to separate the effects of the instrument on the image from the effects of the sun on the image. Okay. So finally, I wanted to go back to my ball bearing and point out that the measurements we're making of the sun's radius and the radius change correspond to the size difference of this ball bearing if I blow on it with my hot breath.
Exclusively sensitive measurements.
And it's possible because we're above the atmosphere and we're doing this from space.
Possible what again?
It's possible only because we're above the Earth's atmosphere and we can do this from space. So that was it. That's my story.
Clarify something that comes up on my screen every day in the morning, and it's
I need a few years.
to get that, yeah, to get it started.
Nice to get 11 years, and that's the plan for that.
You can learn a little something or be reminded of something.
Does that mean we're not going to need the new observatory on the top of Colorado?
Okay, so the question was, do we need an observatory? Do we need to do anything from the ground? And the answer is that while some things are great from space, like measuring the size where we need to get beyond the atmosphere doesn't have much effect on our ability to measure magnetic fields. So that sunspot that you saw, which is making the sun brighter, we don't understand. And the only way to understand that sunspot and the chemistry of the sunspot is to be able to have very fine detailed observations, not of the whole sun, but of a small area of the sun. And so what that telescope does is give us a microscopic view of the features on the surface of the sun that we need to dissect the mechanisms that make the sunspot work. So there's a big picture that we get by looking at a whole image, and then there's the microscope picture that we get from that telescope. Now you say, well, you still have the atmosphere and the blurring of the atmosphere, and you're right, but that telescope is designed with what we call adaptive optics. It's designed with a mirror system that takes out the blurring effects of the atmosphere in the small microscopic view that we can get with the telescope. So it's the complementarity of the microscope view with high precision that lets us look at these small features and understand what's going on, and the overall big global picture, which is required, for example, to know what the sun's radius is. So it's a good complementarity.
So, Jeff, will SDO have a radiance measurement also?
So the Solar Dynamics Observatory, like the Solar Heliospheric Observatory, is actually a federation of observations, a federation of instruments. Our instrument is one of the most complicated, called the Heliomagnetospheric Imager. The other instruments include telescopes that will look at the sun in X-ray and other wavelengths that we can't see from the ground, and also it will have, like the Akram instrument, it will have an instrument to measure the brightness of the sun, which is a really critical thing. Many people are now scratching their heads saying, well, okay, if the sun's radius is changing on a long period of time, is its brightness also changing? And you could see from those figures that we can measure 11-year changes, but to put them all together is rather hard, and we can't rule out from those data whether or not there's a long period trend in the brightness of the sun, like there might be in the radius of the sun.
There's another item. I wonder how big its effect is. I understand the Earth's orbit around the sun changes from circular to elliptical back to circular. This is a 100,000-year period or something like that. Is that because you're measuring on a distance? Is that changing enough so it makes your measurements less valid, or you have that,
Do we
or
have
do
to
we
worry-
understand
we have
this
to worry
one
about-
well enough to?
Okay, so
zero
his
it out?
question was, what about other things in the orbit that are more complicated than just this ellipse? And there are three things that complicate the orbit of the Earth, and they were discovered or talked about in the 1800s by a scientist by the name of, a Russian scientist by the name of Milankovitch. Milankovitch pointed out that the orbit, the amount of energy that the Earth receives is controlled not just by its distance to the sun, but how much of the land mass compared to the ocean mass faces towards the sun. So the amount of energy that the Earth receives depends on, so you know that the Earth's orbit is tilted, and normally it goes around the sun with the axis in the same direction, but not really. That axis precesses like a top with a period of 26,000 years. On top of that, that axis dips up and down, we call that nutation, with a period of, I forget, but tens of thousands of years. And on top of that, the orbit, as you point out, isn't a pure ellipse, but it changes from being more circular or less circular with another period of tens of thousands of years. And all of those effects conspire to produce a cycle and the amount of energy that the Earth absorbs, which is about 100,000 years. Do you know what happens to the Earth's climate on a scale of 100,000 years? We have ice ages. Every 100,000 years, there's a warm period of about 20,000 years. We're in the middle of one of those now. If you go back 100,000 years, there was another warm period. In between, we have ice ages. We're in a very lucky time. It's warm. Within 10,000 years, the average temperature of the Earth will drop by about 10 degrees Celsius.
Maybe we ought to try
Don't get me started. So let me tell you about CO2. We know about these cycles. We know the cycles are caused by the orbital effects and the amount of energy that the Earth absorbs because of the relation of northern hemisphere land to southern hemisphere land and water. We can measure and date the temperature and the carbon dioxide content of the Earth's atmosphere by doing core drillings in the northern and the southern hemisphere. And you can get a core which hits rock that goes down a couple of kilometers. That gives you almost 500,000 years. You can go down, so you can count strata in the first 10,000 years. Sorry, roughly 20,000 years. And then you start getting dates by just knowing how it compresses. You don't see strata, but you still have bubbles. If you pull the bubbles out, you can measure the fraction of CO2. And guess what happened when you got back to the previous interglacial or warm period? What do you think happened to CO2? It went way up. Right? And in between it went way down. And now it went way up. Was the climate warm back at the previous interglacial because of CO2? No, it was warm because of these effects we know about, which are these orbital effects. Is CO2 the cause, or is it an indicator of climate? It's an indicator of climate. You started. If you take,
You and I are on the same page. Keep going.
if you take the record of temperature that the British have been doing since 1840, and they've done it by measuring ocean water temperatures, and it's pretty reliable, it turns out that temperature record goes up, goes flat from 1900 to 1940, and then goes up again. The carbon dioxide record is uniformly going up. Why is it that between 1900 and 1940 it was flat or went down? And why is it between 1840 and 1900 it went up at nearly the same rate as it's going up now, when the carbon dioxide production was enormously different? It was hugely different. Another fact. If you look at the temperature measured over longer time scales by looking at the size of glaciers, and I don't know why they were doing it, but there's a record of glacier lengths. And the lengths of glaciers have been decreasing. But it turns out they started decreasing about 50 years before the CO2 started going up. CO2 is an indicator, not as a cause. Did you know that the amount of CO2 in the Earth's atmosphere, if you go back hundreds of millions of years, was 1,000 times what it is now?
Wow.
Where did it all go? It was the coupling between the oceans and limestone and plants and animals. In order to understand what happens to CO2, you have to understand the oceans and life at a much higher degree than the climate models that we've been sold. I'll stop there.
Shift gears for a second, just ask you about if you speak as to the current state of the heliosphere in regards to the next predicted solar cycle, what could happen?
So we don't know. We failed to understand when the next solar maximum would begin by 20-30% of a solar cycle. So we think we have this rough idea of how magnetism gets recycled inside the sun. So that, remember we said the sun is spinning faster at the equator than it is near the pole. The magnetic fields are like rubber bands, and because the sun is so hot, it's very conducting, and so those magnetic field lines are stretched and rotated and collected inside, and then they get strong enough that they have to pop out again. That's our hand-wavy way of describing what we think is the 11-year cycle. But when we put that into a model, we find we can't predict things. So we have a fundamentally incomplete understanding. We have a fundamentally incomplete understanding because the total irradiance of the sun is brighter when there are more of those dark regions. So I don't have a good answer.
Do you think that in the coming years with some of the galactic lineups, that the effects of the big planets on the sun are going to influence this?
It's hard to make that work.
Would you restate that?
So his question
was
was
about the lineup with the galactic center and the central universe. Or he can explain it better than me, please.
So the question was, could there be other effects like the alignment of the planets or the alignment of the solar system with respect to the galaxy? You should know, you know how long it takes Jupiter to go around the sun? Anybody know? It's about a solar cycle, but it's not exactly a solar cycle. So there are people that talk about alignments as somehow creating the solar effects. That doesn't really work. The gravity interaction is too weak. Jupiter is incredibly regular, and the solar cycle is not regular. It's hard to understand how it works. I can't say that it's not the cause, but it's the gravitational, it's usually tide that we think of. And we know that the sun and the moon affect the Earth in a subtle way. It's the size of the tides. But the effect of distant stars on the sun and the Earth is much, much smaller. And so at best it could be some planetary influences, but nobody I know has anything that
Are we not coming more into alignment with the center of the Milky Way and could be influenced by?
Well, be careful. You know how long it takes to
events that have
but
been
you
found
know how
in
long
the
it
iceberg
takes.
samples?
You know how long it takes to go around the Milky Way where we are?
Well, there's
200 million years.
Long time.
So how are we any closer now than before is what you
Over our lifetime, it's insignificant changes because it takes 200 million years to go all the way around. So the time scale for things to happen in the galaxy is very, very long. And compared to the changes that we look for, it's hard to understand how they work. But who knows? Could be. Yeah.
Different question. Who's the consortium behind who owns it?
We do. We paid for it.
Okay.
It's a NASA satellite. All the data is available to anybody that wants it. It's absolutely free. The primary scientists who designed it are a group at Stanford. I've been involved in it, as I said, for many years, and a large number of other scientists who are actively engaged in using that data. A big part of the science community is involved in it. Yeah.
What's the life expectancy of SOHO and of this one?
So SOHO was originally launched by NASA to have a lifespan of 6 years. We're working on 12.
Bang for the buck.
So, yeah.
Think you're lucky.
Sorry. That's right. We do have to think lucky. And now the cost is just in the operation. Now, we almost lost SOHO on one of the experiments I wanted to do. We told it to roll, but they rolled it and they lost the antennas. And it took about 1.5 years to find it. And when we found it, it took another 3 months to thaw it out again. But we got it back. And that's another testimonial to Lockheed and NASA in the end. But SDO has a design lifetime, again, of about 6 years, if I remember that right. But we need it to last for a solar cycle, and I think it will. So the plan for these 2 satellites is to have them overlap for about a year so we can get the cross-calibration between the 2 instruments, link things up. And then probably SOHO won't be operated because of the expense of the people associated with running.
How do they plan on keeping the lens clean this time, so the lens was dirty?
No, it turns out that's a problem with radiation, and it's really hard to change it. Now, you can change it by using different glasses, and I think that there is an attempt to do that. That front lens, that front window is now going to be temperature controlled in a more sensitive way so that we don't have to. It turns out that if you know optics, the lens, because of the temperature gradient, has a radius of curvature of about 6 kilometers. And that 6 kilometer radius of curvature is
It could be fabricated out.
except it changes.
Yeah.
As the darkening changes, the amount of energy that it absorbs changes, and that's hard. So there's a heater there now to actually regulate that in a careful way. I think I should let you go. If you want to stick around and ask questions, please do. If you want to take off, you're free. And thanks for coming.
Without what?
Yeah, it was nice.
Yeah.